All right, homework 21, we're going to start with explained and unexplained variation and the least squares regression line. First of all, they're going to do a bunch of the calculations for you, but you're going to have 3 different calculations that would normally be done, and you need to know what all of those things are. So the first one, when you have y hat minus the mean of y, is the sum of the squares regression line. They call it SSR, sum of squares, yep, regression. The next one, where you just have y minus y hat is SSE, sum of the squares error. Gives you the error. Sum of squares, you can almost read that S, error. So that one was the SSR. This one is the SSE. The last one, when you have y minus the mean of y with the bar over the top, you have SST, sum of squares total. So on this table here, the sum of the squares regression is 1.83, so forth. Sum of the squares error, 1.9140. Sum of the squares total, 3.7280. So, it says, bivariate data obtained for the paired values x and y are shown below in the table, labeled sample data. Here's my sample data. These data are plotted in a scatter plot in figure 1, so they plotted the points for you. They also put the equation of their regression line, which is y hat equals 1.95 plus 0.44x. So they've done all that work for you. It says in the calculations table, calculations involving observed values of y, the mean value of y, and then the values of y hat are predicted from the regression line. So, for the data point, 3.9, 4.5, the value of the residual is what? Round your answer to at least 2 decimal places. So what they're trying to tell you is really you're not even going to look at the 4.5. You're just going to look at this value here. That is the x value that you want. In your table for your sample data, you got 3.9 and 4.5. But if you put this into your equation for your line of best fit, what value do you get? So you're going to take the number for the x value of that data point, plug it into your equation. So y hat is going to equal 1.95 plus 0.44 times that x value, which is 3.9. And then you're just going to do that calculation. If you multiply all of that out and round your answer to at least 2 decimal places is what it tells you to do. If I grab a calculator here, I get 3.666 when I do that. So if I'm going to go ahead now on this one after I get that number, and now I have to find what the residual value is. So now what I'm going to do is I'm going to take the value that they said was going to be the x value and find what the difference is between those. So what I'm really doing is trying to find what the difference between the point where it would be on my line and the point that would be in my graph would be. So I'm going to say that in my original data point, I had 4.5. On my line of best fit, I had 3.666. I would subtract those two values, and the difference is what your residual value is. So I would get 0.834 when I subtract. Since I'm rounding to two decimal places, 0.83 would be my residual value between those 2 points. So we take the x value from the point, put it into our line of best fit equation to find out what the value on the line would be. And then we take the y value from the point, subtract the y value from the line to see what the difference between those 2 points is. Second part of this question says, the least squares regression line is given above is said to be the line which best fits the sample data. Best fits the sample data. The term best fits is used because the line has an equation that minimizes, and the line of best fit should minimize the error. So I'm going to use SSE here. The line of best fit minimizes your error. So the sum of squares error for these data. And so then what I'm going to do just is look in my table because they've already done my calculation. In this case, it's the 1.9140. 1.9140. So I just looked that number up in my table. That's the number for the sum of the squares error. I got to move my thing because I can't see the bottom two questions here. Hopefully you have that written down. Bottom two parts of this, it says, I'm going to see if I can still keep that table there. The variation in the sample y values is explained by the estimated linear relationship between x and y given by, so when it asks for that, the variation is explained by, that one is going to be your SSR, the sum of the squares regression. The sum of the squares regression explains your variation. And then the same thing, I'm just going to look at my table, and since I moved it, it took off my labels, but this was my regression, this one was my error, this one was my total. So here's my regression. And then I'm just going to look at my table and pick out the number or put the number from that one, 1.8345. Whoops, I got to put it in the right spot. 1.8345. And the last one, it says the proportion of the total variation in the sample y can be explained by the estimated linear relationship between y and x. And in this case, what we're trying to find is what they call r squared. R squared is found by taking the sum of the squares regression number divided by the sum of the squares total number. So I'm again going to just look in my table. My sum of squares regression, 1.8345. My sum of the squares total, 3.7280. I'm going to divide those two numbers, round my answer to two decimal places. So again, if I just grab my calculator, 1.8345 divided by 3.7280 gives me 0.4920, so forth and so on. We're going to round our answer to two decimal places there. So if I round that off to two decimal places, 0.49 would be my answer. So again, just to make sure you have all your answers in here, 0.83 was our answer when we did that one. The sum of the squares error is my best fit, and the number for the sum of the squares error was 1.9140. So we're going to look something like that. All right, number two, pretty close to the same thing. If I move my thing. So in number two, it says bivariate data obtained for the paired values x and y are shown below in the table labeled sample data. So here's my sample data. The points are the points that are plotted over here in figure 1. It also shows you the regression line, the equation for the regression line, which is our line through here, y hat equals 3.06 plus 0.97x. The calculations in the table involve the observed y value, the mean of the y value, and the values of y hat, which are the values from your predicted regression line. So, be careful on here. They switch these around to make sure you're paying attention which is which. So when I have y minus y hat, that one is my sum of squares error. Y minus y hat. When I have y hat minus the mean of y hat minus the mean with the bar, that's the sum of the squares regression, SSR. And then when I have y minus the mean of y, that's my sum of squares total. So you want to watch for that because they switch them around and they don't always put them in the same order. So the variation sample y values that is not explained by the estimated linear relationship between x and y. When it asks you about the variance being not explained, then I am going to do the sum of squares error. Now if you read your chapter for chapter 11, it's going to explain all these things, so you might want to make sure you go back and look. But if it says variation not explained, it's a sum of the squares error. And then again, we're going to just look in our table. In our table here, we have 45.7727. The value of r squared is the proportion of the total variance in the sample y that is explained by the estimated linear relationship for x and y. For these data, what is the value of r squared? So that's the one we did last on the previous one. When we did r squared, we took the sum of the squares regression line and divided it by the sum of the squares total. And so my SSR number was 224.7529. My sum of the squares total number, 267.2120. 267.2120. Again, you're going to grab your calculator and divide out those two numbers. So, 224.7529 divided by 267.2120 gives me an answer of 0.8411, so forth and so on. But we know we only need to round it to 2 decimal places. So if we round that off to 2 decimal places, 0.84 is going to be what our r squared number is. Number 3, it says the least square regression line given above is said to be the line of best fit. Again, if you remember from problem 1, when it talks about the line of best fit, the term best fit is used because the line has an equation that minimizes the error again. So I'm going to have SSE. It minimizes my error. So variation is not explained by the error, and best fit is explained by the error, or is given for the error. So for my SSE number, same number we had before, 45.7727. 45.7727. And then the last one is the one where we did before. We had to find the value of the residual, kind of the distance between those 2 points from our actual dot and the point on our line. So we want to use the data point 590. 590, this data point right here. First thing we're going to do then is figure out if we use our equation and put in 590, what do we get for our y hat value? So y hat is going to be equal to 3.06 plus 0.97 times the x value, 59.0. We're going to find that value first. That's going to be the value of y on our line. Again, we're just going to grab our calculator. And figure that out. 3.06. So I get 60.29. 60.29 would be the y value right on the line at x being 59. So x being 59, here we are, if I could get pretty close anyway. 60.29 would be the y value of that point. Now we're trying to find the residual value between those 2 points, the point that was given and the point that's actually on the line. So on the point that was given, we were at 62.6. If I look right here or look in my table, so I'm going to take my 62.6 and subtract my 60.29. If I take 62.6 and I subtract my 60.29, I get 2.31. So my residual value is 2.31. All right, number 3, going to be the same thing. There we go. Wanted to get it as close to the top of the page as I could. Variant data obtained for the paired values x and y are shown in our table below again. Sample data. These data are plotted in the scatter plots. So each of the points that are made are the data in the table. And then we also have our least squares regression line. They give us that least squares regression line equation right here. The line is also on my table. In the calculations table, the calculations involving y, the mean of y, and the values of y hat, which are the values that we get right here on our line, predicted from the regression equation. So, we had a look. Here we have y minus the mean of y. So y minus the mean of y, if you remember, that's my SST value, sum of squares total. The middle one I take y hat minus the mean of y. Y hat minus the mean of y is my sum of squares regression. And then we have y minus y hat. Y minus y hat is my sum of squares error. So make sure you always look at your table because they switch those around, you get the right ones marked. Number 1, least square regression is given above is said to be the line which best fits the sample data. The term best fit is used because the line has an equation that minimizes, and if you remember from the previous 2, the line of best fit is going to minimize your error, so we're going to have the sum of squares error. Sum of square error number, we're just going to look in our table. 48.4865 is going to be my number there. This one is one we didn't have on number 1 or 2. It says the total variation. Notice the word total gives you a hint. The total variation in the sample is given by the sum of squares total. That makes sense, right? And again, we're just going to pick that number off the table. The number for the sum of squares total is the 297.7680. Next, we're going to do the proportion of the total variance in the sample values that can be explained by the estimator linear relationship of x and y. Again, that proportion is the same thing as when they ask for r squared. So 2 different ways they might ask it. Either they're going to ask for r squared, which is the proportion of the total variation. So proportion, I'm going to set up my fraction. We said we're going to take our SSR value divided by our SST value. The sum of squares regression divided by the sum of squares total. So in this case, we're going to take the 247.9325. We're going to divide it by the sum of square total, which is 297.7680. So we're just going to divide those 2 numbers. Go ahead, grab your calculator, punch that in. And so, I'll just grab my calculator and punch that in. 247.9325 divided by 297.7680. That gives me 0.832634, da 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 da. So, rounding that off to 2 decimal places, we know that we're going to use 0.83. 2 decimal places, 0.83. Last one is where we're calculating that residual. The residual, the distance between the actual given point that we have in our sample data and the point that's on our line of best fit, that equation that we have up there. So we're going to use the data point 138 with 131.7. So we're going to use the x value of 138.0, and we're going to plug it into our equation for our line of best fit, our residual line there. And so y hat is going to equal 196.76 minus 0.50 times, I didn't leave myself enough space, so sneak it in there, the 138.0. That should go times that number behind there when you punch it in. So, I'm going to go ahead and put that in there. And so when I do my calculation, hopefully you had time to do your calculation, I came up with 127.76. So the 127.76 would be the y value of the point that's exactly on the line. We now want to find the residual, so we want to find the difference between the data point that we have here and the point that we found on our line. So now we're going to take our 131.7, subtract our 127.76. And if you go ahead and subtract those numbers, hopefully you end up with 3.94 for the value of your residual. All right, the next ones, we're going to do confidence intervals and prediction intervals from simple linear regression. Again, we're going to have some formulas that we need to know. And so in order to do the prediction interval, my equation there is that I'm going to take y hat, which is my value here when I use my equation that's given in my problem, plus or minus t, we're using the t1 sub alpha divided by 2, and that's just found the same way we did before. We'll talk about that in a minute, times the s value times the square root of 1 plus, and then we have to have the given, or the value here. I'm going to put a whole bunch of x's, but those are asterisks. There, we'll put asterisks. The given value, which is going to be given right over here. So this number, they're going to do the calculation for you. And so when I put 1 plus the given value, the given value is that one that we have right here. All right, so it says, movie studios wishes to determine the relationship between the revenue from the rental of comedies on a DVD and the videotape and the revenue generated from the theatrical release of such movies. The studio has bivariate data from a sample of 12 comedies released over the past 5 years. These data give the revenue X from the theatrical release in millions of dollars and the revenue Y from the DVD and videotape rentals in millions of dollars for each of the 12 movies. The least squares regression equation computed is, and they give us that equation. The studio has plans for the DVD release of a comedy that grossed about $32.6 million in theaters. The studio has predicted the rental revenue from this release using the regression equation and is now interested in both a prediction interval for this rental revenue and a confidence interval for the mean rental revenues of the movie generating the same theater revenue. The studio has already computed the following for their data. The mean square error, which is this value here, and then this crazy value here they computed for you that is going to go over in the formula. Based on this information, assuming the regression assumption holds, answer the questions in the table below. First of all, it tells us that we want to do a 90% prediction interval. That is important because we have to do this right here. So 90% prediction interval again means that 90% is in the middle and we're finding the percent on each end of my expression here. So we do 1 minus 90%. 1 minus 90% would be 10%. We then divide it by 2, so 5% would be on each end. So we know that we're going to do t sub 0.05. Now we know that on our t value, we also have to do the degree of freedom. The degree of freedom on these problems are going to be n minus 2. N, how many comedies in this case? How many movies did we do? We did 12. So 12 minus 2 means we're going to have 10 degrees of freedom. So when we put that in here for the t sub, we're going to have t sub 0.05 with a degree of freedom of 10 is what we want to use. So we got to do our prediction interval for a 90% confidence interval. Value for the rental revenue in millions of dollars when the theater revenue is $32.6 million. So first thing we're going to do is figure out what the y hat value is for 32.6. So we're going to use this equation here and say, okay, y hat is equal to 3.50 plus 0.16 times the 32.6. And we're just going to grab our calculator and figure that out. So again, I'll grab the calculator, put that in there. Hopefully you're doing the same thing. And I'm coming up with a y hat value of 8.716, or 8.7, yep. 8.716. That value here is my y hat value. So I'm going to have 8.716 plus or minus, then my t that we already figured out, t sub 0.05 with a degree of freedom of 10. Click up to the side. We need to find what the S number is. The S number there is, if I'm looking here, we have to find the S number. All right, next part. We have to find what the S value is. The S value is found by taking the square root of the mean of the square error number. Mean of the square error. So we've got to take the square root of 12.80 in order to find S to go in our formula. So if you go ahead and grab your calculator and do the square root of 12.80, I get 3.57777. We're going to carry our intermediate calculations out probably to at least 3 or 4 decimal places. And so I carried it out to the 3.5777. Usually I like to carry it out at least, oh, does it tell me? It does. Carry your intermediate computations to 4 decimal places. So we want to go at least that far. This number here then is going to go in for my S number, 3.5777. On the end of my equation, I'm going to do the square root of 1 plus whatever this number is that they got by doing this big, long, crazy calculation. In this case, 0.0846. Now these ones you've got to do on your LX calculator because you have to do the T sub. So make sure when you punch that in, 8.716 plus or minus T sub 0.05 degrees of freedom of 10. Click up so you're out of the lowercase subscript, and then put times my 3.5777, and then times the square root of 1 plus 0.0846. I'm going to give you a little bit here to get that punched into your LX calculator. And when I did that, I have 1.963 so forth was my lower end, to 15.469 and so forth is my upper end. Again, due to rounding, you may have slightly different answers, but they should be pretty close. We are going to round our answer to only 1 decimal place. So if I'm going to round this to 1 decimal place, I have a 6 behind my 9, which means I have to round that up to a 10. So 1.96 is going to round off to 2.0, right? 1 decimal place, my 9 rounded up to a 10, so I had to carry. And then the other one's easier to round. 15.46, I'm going to round off to 15.5. All right, so that one part of that question, really long because I've got to do a number of calculations in order to find just those 2 values. The next part of the question, it says, choose one response to answer the question below. Consider, but do not actually compute, the 90% confidence interval for the mean rental revenue when the theater revenue is $32.6. How would this confidence interval compare to the prediction interval? So they're asking about how would the confidence interval compare to the prediction interval. What we found here is the prediction interval. On the next problem, we'll do a confidence interval. So, how would they compare, assuming that both intervals are computed from the same sample data? So, when I'm doing this, the confidence interval is usually narrower. The prediction interval is usually the opposite, wider. So I want to think about this one's more narrow, this one's wider, gives you more options. Confidence interval narrower. And in this case then, I'm going to have the same center. So on these ones, when I'm comparing these 2 things, we know we always have the same center. So in your drop down, one of your choices and the answer to this question, because I'm doing the confidence interval first, the confidence interval is narrower, but, whoops, they switched that around on me. The confidence interval, I should start with, has the same center, but is narrower. So when I'm comparing the confidence interval to the prediction interval, the confidence interval is narrower, but we're going to have the same center. So they put the same center first and then the narrower second. Just kind of watch how they word that. If it were switched around and they had the prediction interval first, or ask about the prediction interval, you'd still have the same center, but then it'd be the wider instead of the narrower. Second, or the last part of that question, choose one response again. So it says, for the theater revenue values in this sample, $62.6 million is more extreme than $32.6 million. That is, 62.6 is farther from the sample mean than 32.6. How would a 90% prediction interval for the mean rental revenue when the theater revenue is $62.6 million compared to the 90% prediction interval for the mean rental revenue when the theater revenue is $32.6 million? So, in this case, since I'm comparing two different numbers, you're going to have different centers. Okay? Different centers. So, when you're clicking your answer on your drop down, whichever number is bigger or wider, farther away, notice it says more extreme, you got to pay attention to which one it has. But in this case, it's going to compare the 62.6. The 62.6 was more extreme, so it's wider. And then it's going to have different centers because I compared two different numbers. So it's going to be wider because it's more extreme, and it's going to have different centers because I'm comparing 62.6 to 32.6, and I'm comparing two different values. Whereas up here I was comparing with the same 32.6, that's why they had the same center. All right. Number 5 then. All right, on number 5 here it says an electric utility is examining the relationship between temperature and electricity use in its service region on warm days. The utility has bivariate data detailing the maximum temperature denoted by X in degrees Fahrenheit and the electricity used denoted by Y in thousands of kilowatt hours for a sample of 30 warm days. For these data, the utility has computed the least squares regression equation to be y hat equals 55.51 plus 3.04x. Tomorrow's forecast high temperature is 87 degrees Fahrenheit. With this in mind, utility managers have used the regression equation to predict tomorrow's electricity use. But they're also interested in both a prediction interval for the electricity use and a confidence interval for the mean electricity use on days for which the maximum temperature is 87 degrees Fahrenheit. The managers have computed the following data. So again, they're giving you the mean of square error, and then they're giving you this value that we used in the formula. Based on this information and assuming the regression assumption holds, answers the question in the table below. So on this one, we want to know what is the 90% confidence interval. If you remember on number 4, they asked you for the prediction interval instead of the confidence interval. So the formula is just a little bit different than what we did on number 4. So this time, when we do the confidence interval, if I can squeeze the formula in there. Again, we start with y hat. Then we have our plus or minus. And our t alpha divided by 2 with our degree of freedom, which is n minus 2, just like we did before. We're going to take that times s.
Anyone owning a blue truck, a blue Dodge truck with Lee County license plates, your lights are on in the parking lot. Anyone owning an older blue Dodge truck with Lee County license plates, your lights are on. Thank you.
We take it times s, which we're going to calculate, and we calculated s on the previous one. And then and this is the part that's different on our formula. Here you're just going to have the square root of that given number. On the prediction interval, you have 1 plus the number. So you have to pay attention. Are you doing the confidence interval or are you doing the prediction interval? For the confidence interval, we just use this given number. If we're doing the prediction interval, we add 1 to that number. So that's the difference in the two formulas. So in this one, if we're going to predict this, first of all, we are going to calculate our y hat value for 87 degrees. So we're going to put 87 in there and do our calculation. So we are going to have 55.51 plus 3.04 times 87. And we are going to multiply that out. Got to grab my calculator. And so 55.51 plus 3.04 times our 87 gives us 319.99. That's going to go in for our y hat value, 319.99. Plus or minus, I'm going to put the t down here. Now remember, this here comes from your confidence interval. If I have a 90% confidence interval, that this is 90%, so 100 minus 90 gives me 10%. I have 2 sections on my thing, so I'm going to divide it by 2. So each of these are 5%, and so I'm going to use 0.05 for my subscript. I'm going to go down here even though that continues on. T sub 0.05. My degree of freedom is n minus 2, so I have to figure out here on my data, we did a random sample for 30 warm days, so 30 is my n value. And so I'm going to do 30 minus 2. 30 minus 2 would give me 28 there, right? N minus 2, 30 minus 2 is 28. So you could put 30 minus 2, but I'm just going to put the 28. Now I have to do my S value that I have to multiply by. Remember that the formula for S was that we were taking the square root of the MSE, the mean square error. So we're going to do the square root of 762.57. Square root of 762.57 is 27.614. I'm going to round it off to 7 because we want to do our intermediate calculations to at least 4 decimal places. So this again is going to go behind here, 27.6147, and then again I'm running out of room under my square root, which goes behind there. My square root here again, I don't have the 1 plus that number, I just have that number, so I'm going to do 0.0368. So on your Alex calculator, again, all this should go in one line. I just don't have room to write it here. 319.99, the plus or minus, T sub 0.05 with a degree of freedom of 28. Click up behind there, times my 27.6147, times my square root of 0.0368. Now again, depending on rounding, you may get a slightly different number, but should be pretty close. When I round off to the 1 decimal place, you should be getting 311.0, or at least something very close to that, and 329.0. Again, it does give you some leeway on Alex because of rounding. You could, instead of using this rounded off number, just type in the square root of 72.57 here, and then you may not get your rounding errors. So either way, it should give you at least close to the same answer, and Alex understands that because we're rounding, we might get slightly different answers. All right, so that's that big long calculation for number 1. Now the rest of the part is kind of just answering our questions below. It says, consider but do not actually compute the 90% prediction interval for the individual value for electricity when the maximum temperature is 87. How would the prediction interval compare to the confidence interval? Remember that the prediction interval is always wider and the confidence interval is always narrow. So prediction interval will be wider. So again, you're going to choose that which one you're going to have. When you're comparing with the same temperature, you should have the same center. So it's going to say the prediction interval will have the same center, but be wider. Something to that effect the drop down will say. Prediction interval is always wider. Confidence interval will be narrower. Since I'm using the same temperature, I'm going to have the same center. Part 3. For the maximum temperature values in this sample, 95 degrees Fahrenheit is more extreme than 87 degrees Fahrenheit. That is, 95 is farther from the sample mean. How would the 90% confidence interval for the mean electricity when the maximum temperature is 95 degrees compare to the 90% confidence interval for the maximum electricity when the maximum temperature is 87? So now I'm comparing two different temperatures. I'm going to have different centers, right? So I know I'm going to have a different center. Now you have to pay attention to which one they're asking. They're starting with. Here, they're doing the bigger number. The bigger number is going to give you a wider sample. The smaller number that's closer, right? It told you that the 95 was more extreme. So we're going to have 95 is wider. It's more extreme, but it's going to have a different center. And sometimes they switch those around and they'll say it's a different center and is wider, but those two words will be in there somewhere. If they would have started off with the 87 would have been narrower, but you still would have had a different center. All right, we got one more of those long ones to do here. The well-known psychologist Dr. Elbod, whatever his name is, I don't know him, so he's really not well known, has established what he calls his generalized anxiety GA scale. The GA scale, which is a scale from 0 to 10, measures the general anxiety of an individual with higher GA scores corresponding to more anxiety. Dr. Elbod's assessment of anxiety is based on a variety of measures, both physiological and psychological. There we go. We'd like to make predictions about individual sleep behavior based on their GA scores. We've collected bivariate data that gives the GA score denoted by X and the number of hours of sleep last night denoted by Y for each of the 10 adults participating in the study. There's my N value. N is going to equal 10. The least square regression equation, y hat equals 8.91 minus 3.2x. We have used this equation to predict tonight's sleep time for a woman whose GA score is 6. We're now interested in both a prediction interval for her sleep time and a confidence interval for the mean sleep time of the individuals with her GA score. We have computed the following data. Again, we have the mean square error. We use that to calculate S because we know S is equal to the square root of that mean square error. They also give you this value here, which is going to be part of your formula that I like to put little asterisks on. So, based on this information, what is the 90% confidence interval? So again, on number 6, we're doing the confidence interval instead of the prediction interval, so we don't have to add the 1 under our square root. So confidence interval, we're going to do the y hat plus or minus the t sub alpha divided by 2 with our degree of freedom of n minus 1 times our s value times the square root of whatever that number is that they've already calculated for us. Confidence interval, you use just the number. Prediction interval, we have to add 1 to that number. So watch to see what they're asking for. Again, we have a 90% confidence interval. I'm hoping you remember if it's 90%, we're going to have 10% left over divided by 2. So our t subscript will be 0.05. If I'm going with my degrees of freedom is n minus 2, so 10 minus 2 is going to give me 8 degrees of freedom. I have to start by calculating y hat. Y hat is equal to 8.91 minus 0.32 times our x value. We are using an x value of 6 since we're predicting what that is. It also tells you right here what's the GA score if my x value is 6. So I want to put 6.0 in there, and then again I have to grab my calculator in order to do my calculation. So 8.91 minus 0.32 times 6 gives us 6.99. So now I'm going to substitute that into my formula. 6.99 plus or minus t sub 0.05 with a degree of freedom of 8 times my s value. Again, just to eliminate some of the rounding errors, I maybe wouldn't just calculate that out and round it off even though it tells you you can. You could just put it in this way, square root of 0.570. If you want to calculate it and then use 4 digits at least, that's okay too. And then we want to multiply that by the square root of this number right here, 0.1145. Again, all that should go in one line with this stuff raised up out of that subscript from your t. So 6.99 plus or minus t sub 0.05 with the degree of freedom of 8. Click up to the side times the square root of 0.570 times the square root of 0.1145. So, rounding your answers off to, this one says 2 decimal places. You should be close to 6.52 for your lower limit and 7.47 for your upper limit. Again, it may be slightly different depending on rounding. So if you got something that's very close to that, it's still going to be okay. It's going to count it correct. Part 2. We are going to do the prediction interval. It says consider but do not actually compute the 90% prediction interval for the individual values for sleep time when the GA score is 6. How would the confidence interval compare to the prediction interval? So, on here again, I'm comparing at the same GA score. I know somewhere in there it's going to say it has the same center. On the drop down, you have to watch, does it ask for the prediction interval first or the confidence interval? On this one, it happened to say the prediction interval. So the prediction interval has the same center, and we know the prediction interval is always going to give us a wider answer. The narrower one is the confidence interval. So if it says the prediction interval, you're going to use the word wider. If it says confidence interval, we would have used narrower. Part 3, for the GA score in this sample, if I use 8.1, 8.1 is more extreme than the 6.0 because it's farther from the mean. How would the 90% confidence interval for the mean sleep time when the GA score is 6.0 compare to the 90% confidence interval for the mean sleep time when the GA score is 8.1? So again, pay attention here. On this one, the drop down asks for the 6.0, not the 8.1. We're used to it asking for that first one. It asks for this one. This one is closer because the 8.1 was more extreme, so that smaller number is going to be narrower. But of course, since we're comparing two different values, we're going to have different centers. So just watch that, because here they may use confidence interval instead of prediction interval. Here they may use either one of these two numbers. The 8.1 was more extreme, so it would be wider than the 6.0, which would be narrower. So watch for that, because they will switch those around on you. All right, 7, 8, and 9, we're back to hypothesis tests. When we're doing the hypothesis test for the correlation coefficient and the slope of least squares, we're going to do a t-test. And in order to compute the value of t, which we'll get down here for our test statistic, but the value of our test statistic t is going to be equal to r times the square root of n minus 2 over 1 minus r squared. We'll get into all those, but there's the main formula we're going to use. First of all, we have to figure out our null hypothesis and our alternative hypothesis. Newburgh Park, Florida is a popular beach resort town. Property values are fairly high there, and as such are rather well studied. One topic of study has been the relationship between housing prices and the distance from the beach. For a recent sample of 22 houses, and it's going to be 22 then, sold in Newburgh Park in the past year, the value of the sample correlation coefficient R, relating the variable house price and the distance from the beach, was negative 0.44. So they tell us R is negative 0.44. Test a significant linear relationship between the two variables by doing a hypothesis test regarding the population correlation coefficient P. Assuming that the two variables have a bivariate normal distribution, use a 10% level of significance and perform a two-tailed test. If we are doing a two-tailed test, remember from our previous hypothesis testing, we're testing not equals, right? The one-tailed test had the greater than and the less than. Two-tailed test is a not equals. Therefore, our null hypothesis is P equals 0. And my alternative hypothesis is going to be P does not equal 0. So in this case, those values are always going to equal 0 that we're comparing it to, because we're looking at a line, and if the slope of the line was 0, it'd be that straight across line. It wouldn't have a positive slope or a negative slope. So these values here are always going to be 0. Test statistic. We already said earlier, when we do this test, we're going to do the t-test, and then we're going to compute the value of our t-statistic by using this formula. So t is going to equal negative 0.44 times the square root of n, which is 22. 22 minus 2 over 1 minus a negative 0.44 squared. If I smush that all in there. So make sure here, since this is negative, you've got that parentheses around your negative. And we're going to go ahead and punch that in. on the Alex calculator, or you probably could do it on your regular calculator since there's no T subs and X subs and all of that yet. And so if you get that number there, hopefully you've got that punched in and checked out, 3 decimal places, you should come up with negative 2.191. Negative 2.191. So we are going to do our p-value. So since we're doing our p-value and it's a two-tailed test, remember we're testing greater, we're testing just this side, but we're also going to have the same value on this side since it's a two-tailed test. So I am going to do P of t is greater than our test statistic, which I have to fix on my test statistic because notice this was negative. That means this is the negative 2.9 or 191. This number here would be positive 2.191. So I have to be careful there. If it's a negative, we really want to do the positive if we're testing to the right. Otherwise, you could test to the left and do 1 minus. So 2 ways you could calculate your p-value. Either you could do 1 minus the p of t is greater than negative 2.191, or just do p of t is greater than the positive 2.191. Those 2 calculations, if you try them out, should give you the exact same number. Go ahead, test that out. It should give you the same value because either you're calculating the percent to the left of this point or the percent to the right of that point. And it should be the same percentage. Hopefully, you come up with 0.020. 0.020. Those both should be the same number. Again, since this is a two-tailed test, we either are going to just add those together or multiply by 2 to find the total of the p-value. We have 2% here and 2% here, which means we're going to have 4% altogether. So keep in mind here on that two-tailed test, if you get the negative number, it's this number. If it's a positive number, this number. We're calculating our p-value to the right. So if you have the positive number, you just have that. If you have the negative, you've got to do 1 minus. All right, so a couple ways you could get that number. Now I'm going to compare my p-value to my level of significance. Is 4% greater than or less than 10%? Well, we know that 4% is less than 10%. Now we got to go back to thinking about all those other hypothesis testing we did. When the p-value is less than, if the p-value is less than, do we reject or do we accept the null value? If it's a less than, we're going to reject the null. If it's a greater than, we accept the null. Right? This is our percent of confidence. If I only have 4% confidence and I want to have 10% confidence, I didn't meet that level. 4% is less than 10%. So, we're going to reject the null. This is the not true statement. This is the true statement then. If I reject the null is not true. So it says, based on the information, can we conclude using that 10% level of significance, is there a significant linear relationship between house prices and distances from the beach in New York Park? Can we conclude that there is a significant linear relationship? Well, how we're going to figure that out, and this is probably a little easier than the other hypothesis testing, is if this is true, there is no linear relationship. If the alternative is true, then there is a linear relationship. So can we conclude there is a linear relationship? Yes, because the alternative statement is true. We can conclude that, yes. So a little easier to think about than when we had to test all those numbers and then we had greater thans and less thans. It's either if the null is true, there's no linear relationship, and if the alternative is true, then there is a linear relationship. Number 8 then. In an ongoing economics analysis, the U.S. federal government compares per capita incomes not only among different states, but also for the same state at different times. For the 50 states, the least square regression equation relating the 1,980 per capita income, or the 1980 per capita income and the 1999 per capita income is y hat equals 7.97 plus 1.97x, with x denoting the 1980 per capita income and y denoting the 1999 per capita income. The standard error slope of this least regression line is approximately 1.10. Based on this information, test a significant linear relationship between the variables x and y by doing a hypothesis test regarding the population slope B1. Assume that the variable y follows the normal distribution for each value of x and that the other regression assumptions are satisfied. Use a 0.5 level of significance and perform a two-tailed test. So, number 8 here, we are going to do B1. It tells us right here. If we're doing a two-tailed test, it's either an equal or a not equal, which means our null hypothesis is B sub 1 equals 0, and our alternative hypothesis, B sub 1 does not equal 0. Again, we're going to do a t-test, and whenever we do the t-test, we have to have the degree of freedom. I don't know if I wrote it on there last time, and I'm not sure if you have to put it in the drop-down or not, can't remember. But if you do, you can calculate the degree of freedom. We are going to find the degree of freedom by doing n minus 1, or n minus 2 is our degree of freedom. How many states did we look at? Well, we had 50 states. So we know that n is equal to 50, so our degree of freedom is 50 minus 2, which is 48. So just in case you need to put that in there, we'll calculate that right away. You need it anyway later on. So now we are going to have a different formula because now we're doing a B1 instead of doing the one we did on number 7. So watch, we have different things. Instead of the P, we got B1. To find T, we're going to use B1, which is the slope of our linear regression equation, over SE sub B1. So, the SE sub B1 is that value that they give you for the standard error of the slope. SEB1. That's the number you're going to use for that value. The slope of my linear regression line is this number right here, right? The number in front of our x is our slope. That's going to be the number we use for just plain B1. So when we're calculating T, we're going to use 1.97 divided by 1.10. No big crazy formula, you just need to pick those two numbers out of there. If you go ahead and divide those numbers out, we get 1.791. 1.791. Again, we're thinking about we're doing a two-tailed test here, and we're going to do the critical value. If we're going to do the critical value and we're doing the two-tailed test, we end up having to divide that by 2. So 0.05 divided by 2 would give me 0.025. And that's the value we're going to do for the critical value. So again, when we do critical value, since we're doing the t-test, we do t sub that number. T sub 0.025. If it's a one-tailed test, we use the number given. If it's a two-tailed test, we have to divide that number by 2. Again, we need the degree of freedom. the degree of freedom is going to be 48. So on the LX calculator, you're going to go ahead and do T sub 0.025 with a degree of freedom of 48. When you put that into the LX calculator, you get a value of 2.011. It's a positive number, so we know that's the number on the right. It actually is this number right here, 2.011. It's not the number inside because it's not the percent. It's our critical value for our test point, 2.011. That means this number here is going to be the negative 2.011. Again, if you did the calculation and you got the negative, then the other one should be the positive. They should be the same number. So we want to be between what two numbers? Negative 2.011 and positive 2.011 would be our two values. Then it says, based on the data, can we conclude at the 0.5 level that there is a significant linear relationship between the 1980 per capita income and the 1999? So, remember here, if the null is true, we say that is no relationship. If the alternative is true, then there is a relationship. A strong linear relationship. I get it all in there. So we have to do our test value. Our test value is this number right here, 1.791. The middle section is the null. The two end sections would be the alternative. We want to figure out where that number would be. Is it in one of the ends or is it in the middle? Well, 1.791 would fall in the middle section, right? 1.791 is between these two values. Since 1.791 is between those two values, is in the middle section, this is my true statement. This one is not true then. So my true statement is that there is no linear relationship. It says, based on the data, can we conclude using the 0.5 level that there is a significant linear relationship? No. There is no relationship. We cannot conclude that there is a significant relationship. Number 9, the Cadet is a popular model of a sport utility vehicle known for its relatively high resale value. For a random sample of 28 cadets, there's our N value, which means our degrees of freedom is going to be 28 minus 2, or 26. Each bought new 2 years ago and sold used within the past month. The least squares regression equation relating the two variables mileages denoted by X and used selling price denoted by Y in dollars was Y hat equals 38.23 minus 0.53X. The standard error of slope of this regression equation was approximately 0.42. Based on this information, we're going to test the population slope, the B1 value. And again, we're going to use a 10% level of significance with a two-tailed test. Since it's a two-tailed test, we're using the equals and the not equals. So, B sub 1 either equals 0 or B sub 1 does not equal 0. This one again, since we're doing B sub 1, we just have our equation that T equals B sub 1, which is the slope of your regression equation over the SSE, or the SE B sub 1, which is the least squares regression, which will give you the standard error of the least squares regression, which is the 0.42. So the SEB1 is 0.42. The plane B1 is the slope of this line. Notice the slope of that line is a negative 0.53. So B1 is negative 0.53. So I'm going to do my calculation. I'm going to take negative 0.53. I'm going to divide it by 0.42. There's my calculation. And so when, I didn't do my type of t-test. I better do my type of test. We know that we're doing the t-test. We already figured out our degrees of freedom was 26, so I better fill in that blank. T-test, degrees of freedom of 26. Value of our test statistic. Hopefully by now you've got that calculated out. Negative 0.53 divided by positive 0.42 is negative 1.262. So, again, we have to remember that we're doing a two-tailed test. If this one is negative, we either have to do 1 minus the P of T is greater than negative 1.262. All right, number 9. The Cadet is a popular model of sports utility vehicle known for its relatively high resale value. For a random sample of 28 cadets, each bought new 2 years ago and each sold used within the past month, the least squares regression equation relating the two variable mileages denoted by X and the used selling price denoted by Y in dollars was Y hat equals 38.28 minus 0.53X. The standard error of slope of this linear regression line was approximately 0.42. Based on this information, test for a significant linear relationship between the two variables, doing a hypothesis test regarding the population slope B1. Assume the variable y follows a normal distribution for each value and x of x and that the other regression assumptions are satisfied. Using a 10% level of significance, perform a two-tailed test. So again, we're doing a two-tailed test. We know a two-tailed test, we either have equals or not equals. So the population slope B sub 1 either equals 0 or B sub 1 does not equal 0. Since we're doing the standard error of the slope, we are going to do a t-test. And if we're going to do the t-test, we need to know the degree of freedom. And so we say n, the number of cadets was 28. The degree of freedom then is n minus 2. 28 minus 2 is 26. So my degree of freedom is 26. We then use the formula here for our t value. Since we're doing the population slope, that's the easier one to do. T is equal to B sub 1, which is the slope of your equation, over SE B sub 1, which is the standard error value, which is that one right there. So looking here at my equation, I'm going to find my slope. My slope is the number in front of the x. Keep in mind I have to include the sign. So in this case, my B sub 1 value is going to be negative 0.53. My SE B sub 1 value is going to be 0.42. And so in order to find t, we're going to divide those numbers. Negative 0.53 divided by 0.42. If you go ahead and do that calculation, you will come up with negative 1.262, rounding that to 3 decimal places. So again, we have to remember that we're doing a two-tailed test, that either if this is negative, you're testing to the left, or we could make it positive and test to the right. So when I'm doing my p-value, I can either do 1 minus p of t is greater than the negative 1.262. That gives me this section over here. Or I can do p of t is greater than the positive 1.262, use the right number, positive 1.262. That would give me the number to the right. Those two numbers should be exactly the same. So I'm going to calculate those out. If I calculate those out, I am going to get 0.1091. Either way, I should get 0.1091. My p-value then, I have to do the sum of those two numbers or just multiply it by 2 since I need the percent here and the percent here. We're going to round that off to 3 decimal places, so 0.218. 21.8% is in those two sections. That's what that's saying. I've got 10% or 10.9% here, 10.9% here. I want to compare my p-value to my level of significance. I have a 21.8 level of significance. I'm comparing that to the 10% level of significance, so that's going to be greater than. If my if my p-value is greater than my level of significance, then I'm going to do what with my null hypothesis? Should I reject the null or should I accept the null? Hopefully remember from all our other hypothesis testing, if the p-value is greater, I have a higher percentage of significance, then I'm going to accept whatever the null statement is. Accept the null. This is my true statement. This one then is not true. Again, on these ones, they're going to ask you if there is a significant linear relationship. If the null is true, there's no relationship. If the alternative is true, then there is a relationship. So in this case, based on the information, can we conclude using our 10% level that there is a linear relationship? No, we cannot, because the null was true. All right, 10, 11, and 12, we're just basically going to interpret our regression equation. It says here, an independent mail delivery service wants to study factors that affect the daily gas usage of its delivery trucks. Using data collection from different trucks on various days, a company analyst uses a software to fit a regression model in the form of y hat equals 22.4 plus 6.2 times x sub 1 minus 1.6 times x sub 2 plus x sub 3 plus 0.09 x sub 4. The y is the volume of gasoline used in gallons. X sub 1, weight of the truck in tons. X sub 2, tire pressure in pounds per square inch. X sub 3, weight of the initial package load in hundreds of pounds. X sub 4, the total distance driven while delivering packages in miles. Answer the following questions interpreting X sub 2 in this model. So what they want you to interpret is what is the meaning of that value in front of the X sub 2. It says holding the other variables fixed, what is the average change in daily fuel use for each additional pound of air pressure per square inch used in the tire's truck? Well, what this number means is that there's a negative 1.6, in other words, a decrease of 1.6 in the pounds per square inch in my tire pressure. So they want to know what is the average change. You're not going to put the negative in there. It's a decrease, but you're just going to say the average change is 1.6 gallons. Is this change an increase or a decrease? Well, because that was negative, it was a decrease. Number 11, a real estate company wants to study the relationship between house sales prices and some important predictors of sales. Based on the data from recently sold homes in the area, the variables y equals the sale price in thousands of dollars, x sub 1 the total floor area in square feet, x sub 2 the number of bedrooms, x sub 3 the distance to the nearest high school in miles, are used in the multiple regression equation. The model estimates that y hat is equal to 76 plus 0.083 times x sub 1 plus 18 times x sub 2 minus 7 times x sub 3. Answer the following questions for the interpretation of my x sub 3 in this model. There's my x sub 3. Holding other variables fixed, what is the average change in sale price for each additional mile from the house to the nearest high school? So my sale price, I have to remember up here, is in thousands of dollars. That -7 means it decreases $7,000 for each change there. So, what is my average change? My average change is 7,000 because that was in thousands of dollars. Is that change an increase or a decrease? Well, since that was negative, it was a decrease. And one last one here on this homework page. An independent mail delivery service wants to study factors that affect the daily gas usage of its delivery trucks using the data collected from different trucks on various days. A company analyst uses a software to fit a regression model of the form y hat equals 71.6 plus 5.8 times x sub 1 minus 3.2 times x sub 2 plus 3 times x sub 3 plus 0.5 times x sub 4, where y is the volume of gas used in gallons, x sub 1 is the weight of the truck in tons, x sub 2 is the tire pressure in pounds per square inch, x sub 3 is the weight of the initial package load in hundreds of pounds, x sub 4 is the total distance driven while delivering packages in mileage. In miles. Answer the following questions for the x sub 4 coefficient. So x sub 4 here, I have that number, 0.05. Holding the other variables fixed, what is the average change in daily fuel used for each additional mile that a truck is driven? This is in miles, so I'm just using the 0.05. Wants to know, is that change an increase or a decrease? I have a positive value. That means it's going to increase 0.05 gallons. So, have to pay attention to the labels. If it has hundreds or gallons or tons, what is the question asking? Because sometimes you have to change things. Of course, if it's a positive number, it increases. If it's a negative number, it's decreasing.